Hey guys, we've got a nice short day of notes today, just 2 pages. And if you have already watched the Ed puzzle from yesterday, this stuff's going to seem pretty familiar because he talked about those last 2 groups. So the second page is going to be especially easy. So we have non-metals. Okay, yesterday was all about metals. And so today's all about non-metals. So a huge percent of your body is made out of metals. Or excuse me, non-metals. It is about 97% of your body is made of non-metals. And you might be thinking, well, I thought like 70% of my body was made out of water. Well, what's water made out of? Water is made out of oxygen and hydrogen. Okay, so that's not in conflict with the idea that most of your body is made out of water at all. Okay, so but the other nonmetals that are big percents of your body are carbon, nitrogen, and phosphorus. So just 1, 2, 3, 4, 5 elements make up 97% of your body. So it's kind of pretty high percentage there. And just like metals, nonmetals can form 2 types of bonds. And fortunately for us, one of those kinds of bonds is the same one. Okay, so remember metals could form ionic bonds and metallic bonds. Okay, so ionic bonds were between a metal and a nonmetal. So now we're in the nonmetal section. So there they are again. Okay, so we have those ionic bonds. Okay, no change. They work exactly the same way as we described them with metals. Remember, the metals are usually going to become the positive ion, and the nonmetals are generally going to become the negative ion, because metals would rather give away electrons, and nonmetals would like to take electrons. All right, and the second type of bond nonmetals can form are called covalent bonds. Okay, and these are only between nonmetals. Okay, so if you're bonding with a metal, if you see a metal in the formula at all, it cannot be a covalent bond. Okay, and so the key word on this one is we are going to share electrons. All right, so in ionic bonds, again, if I went back, we were giving away electrons, right? One was giving away electrons and one was taking an electron. So sometimes we say ionic is the transfer of electrons that forms it. Covalent is sharing, okay? And when we form a compound this way, we call them molecules. And they don't, the weird thing is something can be a compound and a molecule, but then we also have, remember, part of our definition of a compound, if I think about that here, has to be made of more than one different element, right? But I could have a molecule with one kind of element, but if I have more than one of them stuck together, for example, oxygen gas that we breathe, okay, it's just oxygen. There's 2 atoms of oxygen bonded together with covalent bonds. So it's a molecule because it's held together with covalent bonds, but it's not a compound because it's only made out of one element. Okay, or we could have molecules that are compounds like carbon dioxide. All right, so we have these covalent bonds holding it together, and it's also got more than one element, so it is a compound. So it's kind of one of those weird, all squares are rhombuses, but not all rhombuses are squares, kind of a description. Okay. And so what holds them together? We said in ionic bonds, it's the opposite charges attract. In covalent bonds, it's kind of the same idea. Okay. So we have shared electrons, and these lines that we're going to use represent those electrons. Okay, so we have the negative of the shared electrons pulls on the positive nuclei holding the atoms together. Remember, atoms all have that positive nucleus with protons and neutrons in it. So the nucleus is out here, it's positive. Another nucleus out here, it's positive. And the electrons that they're sharing are on the inside and they're negative. So the negative's pulling on this positive and the negative's pulling on that positive. And so they kind of are held together that way. All right, so we have this kind of class of molecules called diatomic molecules. Let's look at that name. Okay, the prefix di means two, right? And then atomic is just talking about atoms. So the word diatomic just means two atoms. And that's what they are. They are molecules made of two atoms of the same element. Okay, I already just kind of drew one up there. Oxygen is a diatomic molecule. And so many elements, they will not exist as individual atoms. Okay, if they're by themselves, if I had a singular atom of oxygen, it is extremely unstable and it's going to bond. Okay, it's going to go either bond to another oxygen, bond to a carbon, bond to lots of different things, but you won't find a single plain lonely atom of oxygen. They're too unstable. Okay, so even as plain elements, they're not by themselves. There are 7 elements that are like that. Okay, and so they are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay, those are the 7. And there's 2 ways to remember which 7 elements are always diatomic. Okay, so if I wrote those out in that order on purpose, you can kind of memorize this acronym Brinkelhoff. Right, you can pronounce it Brinkelhoff, Brinkelhoff. Or if you have your periodic table handy, if you can remember that there are 7 of those diatomic molecules, you can start at the 7 and kind of draw the number 7. All right, you see there's the number 7. But that's only 6 elements, right? So if you use the 7 method, you start on 7, draw a 7, there's those elements. You have to remember also hydrogen. Okay, so you can either kind of remember Brinkelhoff or go to the 7, draw 7, and remember that you have to kind of artificially add hydrogen. Okay, so diatomic molecules. So if I said, you know, something reacts with iodine gas, okay, it's not just I, it's I2. It's 2 of them stuck together. Or the oxygen gas that we breathe, it's not just O's, it's O2. Right? It's 2 of them stuck together always. All right, last little half page here for the day here. So again, if you watch the Edpuzzle, this will be a review, but we have noble gases. Okay, they're the ones in what you can call it group 8A, or some periodic tables just call it group 18. And why the name noble? Okay, so if you think back to like medieval times with the kings and queens, okay, are the kings and queens interacting a lot with the common folk, the people who are actually working, the masses, if you will? No, right? They keep to themselves, they stay in their castle, and so the idea of noble gases is kind of like, oh, they're too good to react, right? They're too good to hang out with other elements. They're kind of stuck up, all right? So the noble gases are this very, very last group here, okay? Hydrogen, neon, argon, krypton, xenon, radon, and nobody uses this one, but octium, why not? And so why don't they react? Okay, the question, why don't they react? They don't react, well, why not? Okay, they don't need to. Okay, so things generally react because they're unstable. Noble gases are extremely stable. Okay, and if you can remember from the last chapter, one reason that things are stable is because they have 8 valence electrons. That's kind of like a magic number when we're talking about chemistry, is 8 valence electrons is very stable. Okay. If you, and hopefully you did watch the video where they are throwing alkali metals into water and seeing what happened, they talked about especially the bigger ones like rubidium and cesium. They were in these little glass vials. All right, so there was this little vial here, and then there was the chunk of the metal that they wanted actually to react with the water. And in that space there, they said was argon. They said it's stored under argon conditions. Okay, why in the world would they surround that metal with argon? Okay, because argon is a noble gas. Argon is not going to react. So remember, those alkali metals are super, super reactive. We didn't want them to react until we were ready, right? Because they would react just with the water vapor in the air. So if something is considered very, very, very reactive, okay, so something that it would be dangerous, that it might just react by reacting with stuff just in the air, it is stored in a noble gas container so that it can't react. Right? As long as that very, very, very reactive metal is surrounded by argon, it can't react because it has access to nothing that it will react. All right. All right. So another thing about noble gases is that when electric current is passed through them, they glow. Okay. So what you probably call like neon lights, if you're at like a bar and grill or something, and they have like cool lights that are neon lights, the different colors are actually from all the different noble gases. Right, so if they're not kind of like I think it's the reddish orange is actually neon. If they're not that color, they're not really neon lights. They have some mixture of different noble gases that give lots of cool different colors when we're looking at them. And our last real important group we are going to talk about today are the halogens. And group, either you call it 7A or 17, depending on what periodic table you're using. And these are the most reactive nonmetals. So these nonmetals are extremely reactive. Okay, so think back to our dot diagrams. Halogens, I'll just pick fluorine because why not, would have 7 valence electrons. Okay, if they get one more, they'll be stable. They're so close to being stable, they're going to try to steal an electron from anywhere they can get it. And that would be causing a reaction. Okay, so they're going to try to gain 1 electron. And so if they gain that 1 electron, then they have 8 valence electrons, and then they would be super stable, just like the noble gases. Okay, so remember that 8 valence electrons is a very, very, very stable situation. All right, so in compounds, so when they react, when they steal 1 electron from somewhere, what kind of charge would they have? Okay, so it was neutral. It gained an electron. Electrons are negative, so this would be like it has 0 charge before, and it's going to gain a negative 1 charge electron. Okay, so it's going to have a negative 1 charge. All right, so let's kind of recap the charges we've talked about here so far. Okay, so if I throw my periodic table up here, hopefully that you can see that okay. So these are our noble gases. They will not have a charge ever because they don't react. They're happy by themselves. These guys are going to end up being negative 1 because they're going to gain 1 electron. If they gain 1 electron, then they're going to have the same number as a noble gas. Way over here, we said these guys are going to be plus 1. Okay, because remember, if they lose 1 electron, they'll have the same number of electrons as a noble gas. If you think about this, so it has 3 electrons. If it loses 1, it's just like helium. It's stable. Okay, so either one of these groups is very, very, very reactive because these guys, they're like, I only got to get rid of 1. I'm just going to try to get rid of this 1 electron. I'll be like a noble gas. And these guys are like, I just have to gain 1. I gain 1, I'm like a noble gas. I'll be so stable. Okay, and then as we go further in, so this is positive 1 and negative 1. Then if we went in a group, these are going to be positive 2 because they have to lose 2 electrons. And these are going to be negative 2 because they're going to have to gain 2 electrons. And we could kind of continue that, except we're going to jump all the way from here to here. So these would be plus 3s all the way down that whole group, and negative 3s. Okay, so hopefully that's just kind of a preview. We'll use that information a little bit more later. But there is our section about the nonmetals. It's a nice short one. Thanks, guys.